This is my first talk in person in over 2 years or so it's a little odd experiencing everything in 3D. My apologies if I'm a bit rusty, and please let me know if I need to speak louder for the video. Looking at the normal seminars, this of course is a bit out of family with what you normally hear about today. I won't be talking, you won't hear me say anything about dark matter or galaxy formation or redshifts. The topic is obviously alien oceans and search for life in the depths of space, which, shameless plug, is actually a book that I published with Princeton University Press on this day, April 7th, 2020. It came out, which was not a good day for a book to come out because the pandemic was going wild. But in connection to the Institute here, there are a few things that I want to highlight, which is that I, in part, got into this field through wonderful conversations when I was quite young in undergrad with Freeman Dyson. He was a visiting professor at Dartmouth College, and at that time, very few of the professors there were endorsing my interest in the search for life beyond Earth. And Freeman and I would have occasional conversations on this topic, and he was so generous with his time. And of course, he passed away in 2020, and just a tremendous loss, but obviously somebody who was dedicated to not just rigorous scientific thinking, but also creativity and thinking about some of these big picture questions. Related to that, I did, my earliest work was on the late time light curve with Sterling Colgate out of Los Alamos. Some of you may know Sterling or have known of him. He passed away in 2013. And Sterling was a bit bashful about his interest in the search for life elsewhere. But he and I would occasionally have these wonderful conversations about the search for life on Mars. And somewhere in my files, I actually have a draft manuscript that he wrote about the search for life on Mars, which obviously was never published. And lastly, as Misha mentioned, Chris Jaiba, who brought me here to Princeton late in my graduate career, I was a visiting scholar in astrophysics. And so with great thanks to these mentors for buoying my interest in not just the search for life, but also focusing in on Europa. So when we think about the search for life beyond Earth, it really is the story of our beautiful blue marble reaching out into the solar system. And this graphic, created by National Geographic, shows a line for each of the spacecraft that we've sent out into our solar system. The faded lines were failed missions. The brighter hues were successful missions. And as you can see, there's many lines that go to Mars and the Moon and Venus even. But there's just a few lines that head out beyond the asteroid belt. These are missions with names like Pioneer, and Voyager, Galileo, and Cassini. And by merit of these few missions, I think one of the most profound discoveries that we've made in the past roughly 60 years of our robotic exploration of the solar system is that we now have good reason to predict that oceans are a relatively common planetary phenomenon. And shown here is the portrait of the ocean worlds of our solar system. There may be more, but these 6 moons around the Earth with the ocean that we know and love and need to protect, obviously. These 6 moons, Europa, Ganymede, and Callisto, 3 moons of Jupiter, Enceladus and Titan, 2 moons of Saturn, and I've even included Triton here, a curious moon of Neptune. These are moons that are covered in ice, and in the case of Titan, an atmosphere also. But beneath their icy shells are these liquid water oceans that in many cases exist today, and as such could provide a nice refuge for life existing today. And the discovery of these worlds has really changed our understanding of what it means for a world to be habitable. As of course you appreciate, in the early days of astronomy and planetary science, our framework for habitability was largely defined by the habitable zone, i.e. you had to be at just the right distance from your parent star so as to sustain liquid water on the surface, so that you could have an ocean that then gave rise to life and so on and so forth. If you're too close like Venus, you lost any water if you're if you were too far away, like Mars, you were too cold and water was either lost to space or froze out. This story is actually a lot more complicated, obviously, but suffice to say that this was kind of a Goldilocks framework for habitability based on the distance from your parent star. And these ocean worlds of the outer solar system are teaching us that this is an old Goldilocks. There's a new Goldilocks in town where the energy to maintain and sustain liquid water oceans comes not from your parent star, but rather from the tidal tug and pull of these moons orbiting their gas giant primaries. And there's no better example of the power of this process than Jupiter's innermost large moon, Io, shown here in the foreground with a volcanic eruption occurring on the North Pole. And so the four large moons of Jupiter provide this kind of new Goldilocks framework. Io, the most volcanically active body in the solar system, lost any water that it once had. Callisto, the furthest out of the large moons, may well have an ocean, but it really doesn't have much in the way of tidal energy dissipation. If it does, in fact, have liquid water, it's likely sustained through radiogenic decay. But in the center, we've got Europa and Ganymede. And Europa in particular may occupy this new sweet spot of habitability, where it's got just the right amount of tidal energy dissipation to sustain this global liquid water ocean in contact with a rocky seafloor overlain by a relatively thin ice shell. And by relatively thin, I mean a few kilometers to perhaps some predict as many as 20 kilometers. But we think that the ice shell serves as a window into the ocean below. So by looking at the surface ice and potentially even sampling the surface ice, we can perhaps get a sample of the ocean. But just to give a sense of how much energy we're talking about, on Earth, we're looking at about 60 to 80 milliwatts per square meter across our seafloor. On Io, we're at 2,500 milliwatts per square meter. Europa, the estimates range from about 10 milliwatts per square meter, which would be just radiogenic decay, up to as much as about 800 milliwatts per square meter. And at Enceladus, as I'll get into, there, the heating is predominantly out of the South Polar region, and that amounts to about 16 gigawatts. The kind of the flux is a little harder to constrain, but nevertheless, you see that relative to Earth, we're actually talking about quite active bodies.
Just for clarification, but in the case of Earth, the flux is down. In the case of the other ones, the flux is up, right?
No, this is coming out of the seafloor. So think about
this is not the solar flux.
That's right, exactly. So this ignores the solar flux. Thank you. And so you can think of at hydrothermal vents along the axial ridges and things are much higher, but on average, this is the oceanic seafloor flux. Now, you might say, well, okay, that's great, but over time, orbits circularize and you get tidal locking, and so eventually that energy cannot last. But that's where orbital resonances are particularly interesting. In the Jovian system, it's somewhat easy to explain. There's a Laplace resonance, a resonance between Io, Europa, and Ganymede that provides a forced eccentricity that maintains the radial tides. And so for every 2 times that Io goes around Jupiter, Europa goes around once. For every 2 times Europa goes around Jupiter, Ganymede goes around once. Callisto, with that big red X, is not yet part of this resonance. But this Laplace resonance is what has helped sustain tidal heating through time in the Jovian system. The Saturnian system is a bit more complicated, and I'll get into a little bit of this later because there's still a lot of question marks. But there have been a variety of resonances through time, and shown here is one plot by Meyer and Wisdom from 2007, showing billions of years into the past, and then Minos, Enceladus, Tethys, Dione, and Rhea as a function of migration distance out from Saturn, where that S dotted line there is the distance within which, if Minos were originally positioned there at the origin of the solar system, it would have migrated inward instead of outward. And currently,
Okay, just one question that in the case of the Earth, I suppose radioactive heating from the interior is more important than tides, but here radioactive heating is not important in the satellites.
So in the case of Europa, which is one of the more rocky moons, the radiogenic decay ends up being about 10 milliwatts per square meter. That's comparable to Earth's moon. With a moon like Enceladus, which is about 1.6 grams per cubic centimeter, a lot less rock, a lot fewer heavier elements, and so much less radiogenic decay. But that's where Callisto is kind of interesting, because the modeling indicates that Callisto might have enough rocky, heavier elements so as to potentially at least sustain some slush layer, even without tidal heating. And there have, focusing on tidal energy dissipation, there are a number of articles out there about rogue planets. Dave Stevenson, long been an advocate of these, where you can imagine rocky planets ejected from the solar system due to instabilities, and eventually they ice over, but through radiogenic decay, you might actually sustain subsurface liquid water by merit of that radiogenic decay. But here, to maintain, in the case of Europa, an ocean that's about 100 kilometers deep, the predominant energy source is the tides.
And in the case of the Earth, what is the partition of energy coming from radioactive decay and from the passive cooling?
I don't know off the top of my head. It's that passive cooling is still left over from accretion, and in terms of milliwatts per square meter, I don't know that off the top of my head. So today, Enceladus and Dione are currently in a 2-1 resonance, and so that has been used to explain some of the heating, but as I'll get into later, it cannot sufficiently explain the incredible amount of heating that Enceladus is currently displaying in the South Pole. So just to put this in context, of course, part of what makes this so interesting is that our search for life is largely guided by the search for liquid water, because wherever we find liquid water on Earth, we find life, whether it's the deep sea hydrothermal vents shown here on the left, or the dry valleys of Antarctica, or hot springs in the Rift Valley of Africa. All life on Earth depends on liquid water, from the tiniest of microbe to the strangest of rock star. And part of why I like to show this slide is that for all of the diversity of life on Earth, we're all connected by the same tree of life. This is the most recent, or one of the most recent maps of our tree of life, showing the 3 domains: the eukaryotes, the bacteria, and the archaea. Reference Mick and Keith are down there. And all life on Earth works on that DNA, RNA, protein, ATP, even paradigm. And part of what makes these alien oceans beyond Earth so interesting is that these are worlds where life could be alive today, and we could probe this question of whether or not there is some other game in town to get the business of life done. And I contrast that with Mars. I do a fair amount of work on Mars. I was a campaign science lead for the first year of roving, the Perseverance rover, shown here in Jezero Crater on Mars. And you can see those 2 little holes in that rock at the bottom center. We've now collected 8 rocky cores from this region of Mars. And some of those cores will get sent back to Earth. Those cores will be used to answer questions about the age of Mars and whether or not there's any biosignatures, any isotopic or old organics in there that could be indicative of past life on Mars. The issue there, though, is that if we use Earth as a model, we're not likely to find much in the way of large structural molecules. You can see in this timeline here, we go back to the Hadean on the left, 4.5 billion years ago, and then today on the right. The molecules that tell us about how life works, the DNA and the proteins, they only last of order tens of millions of years in the rock record on Earth. When we look at Archean rocks, some of the oldest rocks on Earth, we're limited to isotopic evidence. And if we go a little bit earlier in time to the Proterozoic, If we're lucky, we can extract some lipids, some ancient membrane molecules from some of those rocks that are about 1.5 or so billion years old. And so we might find some of those molecules in rocks on Mars, but that's not going to tell us about the genetic history of that life and whether or not it has the same origin as life here on Earth, or whether or not it represents a second origin. And that to me is really critical, because what's driving my interest and the interest of many of us in the field is this simple question of, is the origin of life easy or hard? And as such, does life arise wherever the conditions are right? And I worry that our efforts to grab ancient rocks on Mars does not necessarily help answer that question, in part because of this issue that I just presented, but also because Earth and Mars were transferring material back and forth from each other in the early solar system. And so without a sharp genetic tether, we might not be able to distinguish whether biosignatures on Mars, were they to be found, were in fact representative of a separate origin or just life that was transferred from Earth to Mars or vice versa. And related to this, part of how this search can help, part of what motivates this search is to better understand our origins. When we think about our understanding of the origin of life on Earth, we've got this kind of bottom-up approach looking at those ancient rocks that I just mentioned. And then we've got a top-down approach where you dissect that tree of life and all the molecules in it to the most fundamentals. And what happens is that you end up hitting this gap between prebiotic chemistry and the pre-RNA world. And that gap then has advocates from many different modalities for that chemistry. A long-standing pillar has been the primordial soup, first popularized by Stanley Miller and Harold Urey. More recently, hot springs and hydrothermal vents have come into play, but we really do not know what happened in this gap. And so were we to explore rigorously these alien oceans, we could engage in a bit of comparative origins and understand the contingent versus convergent aspects of chemical evolution. And shown here are one block, the primordial soup. That modality for the origin of life requires continents with rocks on which tides can lap and then recede, and desiccation can occur and molecules can bind together. A sun, potentially some hot springs. There's hydrothermal vents, deep ocean chemical reactors that are alkaline and have various metals on which organics might be catalyzed. There's also the possibility that maybe life does have a cold or icy origins. That's poorly explored. And then, of course, there's the kind of get out of jail free card, which is planetary transfer. But that's of little utility because it just pushes the question backward. Were we to go to a moon like Europa and find life or not find life, we would at least have a second data point on these modalities. There's no continents on Europa. If life did arise on Europa, it would have had to have been through hydrothermal origins or through a cold, icy origins. And that can help inform our understanding of how life on Earth originated. And by merit of being so much further out in the solar system, even if life on Europa were based on DNA, I think that would indicate potentially a convergent chemical evolution towards DNA as a molecule for getting the business of life done. And coupled with this, these alien oceans have a variety of different chemistries, which someday, centuries from now, I think if we do find life beyond Earth, it's within our own solar system or beyond, we might start to assemble something akin to a periodic table. And that would be organized through variations in solvents and this kind of branching network that I've outlined on the left there. And in this case, worlds like Europa, Enceladus, and Ganymede provide liquid water environments, which is a polar solvent, and then perhaps worlds in which carbon life and variations on that could occur. But meanwhile, Titan, which I won't get into much today, provides these liquid methane and ethane lakes, which is a non-polar solvent. And who knows, perhaps biology can get the business of life done using a non-polar solvent. We just have to go out there and explore to see whether or not anything is actually happening out there. And so when I think about how to categorize these alien oceans, Europa and Enceladus really rise to the top in terms of a new Goldilocks. These are worlds where we have pretty solid evidence of liquid water oceans in contact with rocky seafloors, overlain by relatively thin ice shelves. And so I'll focus much of the rest of my talk on these two worlds. Titan, as I alluded to in the previous slide, is a great place for thinking about weird life, life unlike life as we know it. Ganymede, Callisto, and to some extent Titan may have these subsurface liquid water oceans, but they're perhaps too big and the ice is too thick. And so in the case of Ganymede, we're talking about roughly 100 kilometers or so of ice. The ice isn't going to serve as a window into the ocean below that well, and we're going to have a hard time getting through it anytime in the near future. That's not to say that life couldn't rise there. Perhaps more of a bottleneck is that the pressure at depth within these worlds is such that the seafloors are made of higher phases of ice, things like ice 4 and ice 6, which means that you don't get the water-rock interaction that provides the leaching and geochemistry needed to perhaps give rise to life and sustain life. So you've got water sandwiched between an ice 1 layer on top and a higher phase ice layer at the bottom.
What about Callisto? Because it's not so well differentiated. Right?
Yeah, so a lot of question marks with Callisto, exactly. And there's, there are, even for Titan also, as you can see here, there's big question marks about differentiation. And so there are certainly some caveats to this in terms of, might you have more of a rocky, icy mess in the material, which could give way to those kinds of reactions. Then there are relic oceans. The asteroid former planet series has got evidence of salt on the surface, and that could be indicative of a liquid water region that existed below the surface. Mars, of course, as I mentioned, well, I didn't allude to its ocean, but we think Mars did have an ocean billions of years ago. And then Triton and Pluto I kind of put in this unknown category because we still are relatively limited in the data. Okay, with that, I'm going to dive into Enceladus and Europa. Enceladus is a very curious moon. It's only about 500 kilometers in diameter, but as you can see from this image, the northern hemisphere is dominated by impacts. And in planetary science, impacts are an indicator of old age. If you just do the crater counts, the northern hemisphere of Enceladus comes out to be about 3.5 billion years old. The south, there's essentially no craters. And you see these curious fractures dominating the south polar region. As I mentioned, it's relatively small, that's just for scale. And along those tiger stripes are these jets erupting out of these fractures. And throughout the Cassini campaign, throughout the flybys of Enceladus that the Cassini spacecraft did, the spacecraft was directed lower and lower and closer proximity to this south polar region and through the plumes directly. Now, even though those plumes look quite dramatic with the reflected sunlight coming off of them, when you look straight down at Enceladus along those tiger stripe fractures, you don't actually see a cloud of Enceladian snow, but you can, if you look in the middle at the lower part of this image, you'll see some softening of the surface. So we think that a jet may be coming out of one of those darker crevasses there, and part of why that region in that area is quite soft is because snow is precipitating out. I shouldn't say precipitating; it's just falling out and covering up some of the fractures. So, what did the Cassini spacecraft find? Well, let's start at the upper left here. With the first few flybys, with the first tastes of these plumes, the Cassini spacecraft, which had 2 mass spectrometers on board, returned the mass spectrum that you see at upper left. Methane, water vapor, perhaps some simple organics, carbon monoxide, perhaps some fragments of complex organics, and some carbon dioxide. And that got everybody's interest, but the combination of jets plus this menu of molecules wasn't that convincing with respect to a subsurface liquid water ocean. And that's in part because both jets and this menu of molecules are seen on comets. And so rather than going to that extraordinary claim of a subsurface liquid water ocean, for a time period there, part of the scientific community held back on drawing the conclusion that these jets were directly connected to any liquid water ocean. But then in subsequent flybys, the mass spectrum in the middle was returned by the cosmic dust analyzer. And what this mass spectrum shows is salt grains coming out of those plumes. Some of the initial collection of the grains came from the E-ring, which is actually sourced by the plumes in Enceladus. And then later, there were direct capture of plume particles right above Saturn by the CDA, the cosmic dust analyzer. And so the recognition that salts were part of the composition of these grains really necessitated some sort of water-rock interaction. You don't get salts on a body without liquid water leaching through rocky materials. And so with that evidence, the case started to build for a subsurface liquid water ocean. That led to the model shown on the upper right there. And then with a few more flybys, it was revealed that silicon and oxygen were in quite abundance directly out of some of the particles in the plumes, and that's shown at the bottom right. That silicon and oxygen signal is interpreted as silicon, SiO2. And one of the best explanations for silica in the plume particles is hydrothermal activity, alkaline hydrothermal activity, perhaps akin to what we see along the mid-Atlantic rise at Lost City, which is a serpentinizing system that is low temperature hydrothermal activity, generating lots of carbonates, and is also implicated as the type of site that may have been conducive to the origin of life.
So this middle plot, this is a mass spectrometry, right?
That's right. And so it's a time of flight mass
charged ions, which have been, I mean, these particles have been charged by the solar UV, and then you.
Well, so
It's local cosmic rays that are doing the ionization.
no, the ionization occurs within the mass spectrometer. So this is capturing it, and then in this case, so this is actually a bucket. The second it blasts it off, and then there's a grid that bends the path of the.
How are they ionized?
So these both through the impact. There's not an ionization that occurs through in the case of the plume particles directed directly. That's
wait a second. So these are big
these are
they're still microscopic particles, but then they are broken essentially into this constituent.
That's right.
Molecules.
Yeah, and apologies. So the dust analyzer is this brass bucket, and it's just ramming through these plumes. The INMS, the ion neutral mass spectrometer, collects neutrals, INMS, and that's the mass spectrum shown at upper left. And so these dust grains are nanometers in scale, and then they get broken apart. And so the last piece of the puzzle, the most recent analyses with the INMS have indicated hydrogen in excess at the plumes. And the hydrogen excess also is consistent with serpentinization, with low temperature hydrothermalism occurring within Enceladus. So all of that, I should say, so more recently, a student of mine, a brilliant student, Jonah Peter, who's now a grad student up at Harvard, I asked him to actually take a look at the INMS data and do an independent analysis of the composition because, I'm sorry.
Yeah, I was just going back, you mentioned that the north and the south were very different and the plumes were just in the south. This is understood why this is so, and does it say anything about what's underneath?
Yeah, that is one of the biggest questions that has come out of the Cassini investigations of Enceladus. One reply is polar wander. So essentially, you get this lower density region, perhaps initiated by an impact somewhere on Enceladus. and then that creates a gravity anomaly that then migrates either to the north or the south. And so it just happened to go to the south instead of the north. That's a fine hypothesis. The model kind of works. I find it a little unsatisfactory because anytime in planetary science where you have to implicate an impact, it's kind of like a get out of jail free card, but it's somewhat viable. And some of the last flybys of Enceladus do indicate that there might actually be a hint of activity towards the north. Yeah, that dichotomy is not particularly well understood yet. So this slide is just to show some of what we've done to dissect the INMS spectra shown in the upper left there, and do quite a parsimonious approach to what might actually be there. And what's interesting is that there are indications of not just carbon-rich compounds, but also nitrogen-rich and things like formaldehyde that when you start to polymerize that, you can actually get towards some compounds that are interesting to the origin of life. So this is our current conception of what Enceladus looks like. These jets at the South Pole. The ocean is thought to be global. The ice would be thinner at the South Pole and then thicker towards the north. But following on the question there, we still don't have a good understanding about exactly why this dichotomy persists.
Sure. Do you know what is a density in the plumes? For example, do we understand if they are hydrodynamic or they are kinetic? What does it mean free path?
I don't know what the mean free path is, but at least in the area where Cassini has been sampling them at about the roughly 100-kilometer altitude to many of the flybys are 500 kilometers, it's kinetic. Yeah, no.
Do you know the density then?
I do not. No, not off the top of my head. But again, when you look at just straight down, the optical depth is essentially zero. You're looking right through the plumes.
Yeah, I'm not talking about optical depth.
Yeah.
Okay.
Yeah. But interestingly, we have looked at coming down with a lander to those plumes, which of course, as you start to get closer and closer, now you need to think about the turbulence associated with the plumes coming straight out.
Yeah, just if it's hydrodynamic flow, I mean, the thickness of the ice will tell you something about how it's launched and so on, right? Because I mean, you need to have some pressure difference going through this.
Well, and the thinking is basically that what's driving it is boiling, and so the fracture is connecting you directly to the water, and then that's the energy that's driving the ejection. And there are some interesting models published of the crevasse dynamics. I'm not, I don't know the details of those, but by Brilliant, I think is the last name. So just coming back to the big picture on Enceladus, I mentioned the resonances through time, and there's a problem with Enceladus, and it's that problem is in part indicated by nothing less than the rings of Saturn. And the issue is as follows. So when you think about the tidal quality factor, this factor that captures how much energy can be released in a given tide. The work by Myron Wisdom, they modeled the mid-sized moons of Saturn, and as I showed in that previous plot, set minus as close as they could to Saturn without it migrating inward. And anything less than a Q of 18,000, they could not yield these mid-sized moons being primordial. Now, the problem with that is that with these moons being primordial and the Q being 18,000, they don't get enough modern day heating at Enceladus. More recently, there have been some analyses of archival data and the Cassini observations that show some tidal recession of the mid-sized moons, and a Q of 1700 is consistent with that tidal recession. But those models and those observations, because the Q is so much lower, require these mid-sized moons to be very young, of order 100 million years old. And in this case, you would actually end up with enough energy to supply the roughly 15 gigawatts of dissipation that you see in the south polar terrain.
But then just mentioned that the north part of Enceladus is 3.5 billion years old.
Well, but so then, right, this is why I hate to invoke impacts, because in this case, right, so in the case where the mid-sized moons are young, what creates a mid-sized moon is some sort of Kuiper belt object or some collision between an earlier epoch of moons, and the impacts that we see on Enceladus and many of the other moons are now much more recent. And so that cratering count clock is not indicative of the full history of the solar system, but rather is the fingerprint of this cataclysm that perhaps created the rings of Saturn and moons like Enceladus. You can understand my frustration with impacts. So, but the tidal cue here and the connection to the archival data, I find quite compelling. And so, what this leads to is a debate: is Enceladus 4.5 billion years old, or 4 billion years old, or is it just roughly 100 million years old? And from a habitability standpoint, if Enceladus is just 100 million years old, would life have had enough time to originate? And would Enceladus be stable enough to have sustained habitability over a long period? We don't know. This is kind of where the field is at right now. There's a good debate going on between or within the field about how old Enceladus is. I should mention, so Chris and I took a look at the heating problem a while back and examined whether or not Joule heating by currents coming down through the Alfvén wings and through the ocean and by Meredith Lorentz force could have supplied a significant fraction of the heating. It does not. We get about 10 to 20 gigawatts or 10 to 0.15 to 50 megawatts, which is much smaller than 10 to 20 gigawatts. And I'll also just, that's the next slide. So let's move on to Europa now. So Europa is a much bigger moon. It's about 3,000 kilometers in diameter, about the size of our own moon, but of course it orbits Jupiter, which is some 318 times as massive as the Earth. Unlike Enceladus, where the ocean was jumping out at us through the jets, and the Cassini spacecraft was able to sample those jets, the Galileo spacecraft, which orbited Jupiter and flew by Europa many times in the 90s and early 2000s, did not find jets. However, the physics of the discovery of Europa's ocean is quite solid. I like to break it down into 3 easy pieces. Find a rainbow connection, basically spectroscopy to determine that the surface is made of water ice. Babysit a spacecraft, look at the gravity data. That tells you about the interior structure. And there's some water layer that extends down for about 100 to 200 kilometers. And the last piece of the puzzle is, I like to make the analogy to adhering to airport security. The Galileo spacecraft discovered an induced magnetic field rising and falling as a result of Jupiter's primary field. And that induced magnetic field is best explained at Europa by a salty liquid water ocean near the surface. I won't go into any more detail on this. My book has got a number of chapters on this. I will also point you to some other papers that Chris and I have published that have gone into all sorts of curiosities and interesting things on rotation of magnetic fields, induction and Joule heating. But I don't have time to go into those today. I'll actually put Chris on the spot to come back at some point and detail that.
Didn't Ganymede also have this magnetic signature? So
Ganymede has got an intrinsic field, which implicates some sort of molten core that has got a magnetohydrodynamic dynamo. And so very curious. And as I'll mention at the end of my talk, the European Space Agency has got a mission going out there in the latter part of this decade that will fly by Europa and then go into orbit around Ganymede.
Is it bipolar? The field?
Approximately, yeah. And it also has an induced component that comes in response from the Jovian field. And actually that the intrinsic field has been implicated in some of the chemistry that we see at the surface. in terms of where water is sort of frostier, and the intrinsic field may actually be protecting parts of Ganymede from more radiation processing. Okay, so just looking at the clock, I want to speed things up a little bit. This is our picture for Europa. Icy shell, kilometers in thickness, ocean 100 kilometers, and a rocky seafloor. The ice of Europa is quite a bit different from Enceladus. We see these rafting blocks, we see these fractures, these arcuate fractures and freckles, these lenticulae that you see, these kind of dimples. Far fewer craters on Europa. Globally, there's just a paucity of crater that puts Europa's surface age at somewhere between 10 and 100 million years old.
What do the colors mean here?
Thank you. That's exactly where I'm going. So one of the things that you'll notice is that unlike Enceladus, Europa's got this strange coloration on it. And in the early days of the Galileo mission, there was a lot of interest in those colors because, as you can see, they're predominantly along these fractures. And so the thinking was, if these fractures are supplying material, allowing material from below to come up, perhaps this discoloration or this colored ice is indicative of oceanic material. And so the spectroscopy from the Galileo mission was done by the near-infrared mapping spectrometer, that thick line shown at top, the NIMS spectrometer. And a great debate ensued where some folks said that the spectra from NIMS indicated a frozen salty brine like magnesium sulfate. And that magnesium sulfate brine is indicative of endogenous material, salts from the ocean below. That obviously is a pretty significant claim. Meanwhile, perhaps a less ambitious and conservative hypothesis was that we can explain these spectra well by sulfuric acid hydrate, H2SO4, plus some water molecules. And you might say, where the heck would sulfuric acid hydrate come from? Io is spewing out sulfur from its volcanism. That sulfur enters the Io torus and then gets implanted on the surface of Europa. And the radiolytic processing of that sulfur with H2O and the ice on the surface yields the H2SO4, the hydrated sulfuric acid. And so one could argue that that those spectra are not sufficient in spectroscopic resolution as to necessitate magnesium sulfate hydrate. And the more conservative hypothesis, and the one that's warranted perhaps better by the data, is the sulfuric acid hydrate. And so when we think about what is the composition of this dark material, we can say with a decent degree of confidence that the H2SO4 hydrate is at least some fraction of that dark material. A lot of the sulfur bombards the trailing hemisphere of Europa, and we see more of that reddish material on the trailing hemisphere. And so that's at least consistent with a sulfuric acid explanation for some of that dark material.
Why would it be correlated with the cracks?
Good. So stay tuned. So I'll get to that with something else altogether. So then, as I mentioned, there's this NGSO4 hydrate. Some still argue for it. I think it's a question mark. My colleague Mike Brown and I took a look at, we used some ground-based data that we collected at the Keck telescopes, and we implicated endogenous magnesium and exogenous sulfur. I won't get into that. What I want to focus on is something else altogether. And for that something else altogether, just a quick trip down memory lane here. Anyway, because my research sent me down this lane. We all, of course, appreciate that once upon a time we be on the cathode ray tubes, and that was an electron gun scanning across phosphors, shown right here, the red, green, and blue. It turns out that scaling the image of a large TV was quite a challenge because you're limited by the luminescence of your phosphors. And so if you wanted to get a much larger screen, the CRT was not a good solution. And in the sort of pre-World War II timeframe, there was another approach to television that was being examined by the Navy and other parts of the military. It's called the skiatron, and as best as I can tell, the skiatron derives its name from the fact that it was focused on utilization of scotophores, which instead of phosphors, scotophores, darken with radiation processing. And the skiatron, the console is shown there at left. And what they use is a layer of alkali halides, which can capture electrons and darken or discolor as a function of accumulated radiation dose. And you can see one of them in use. I think that's in sub there. The beauty of the skiatron, the diagram here. So you've essentially got a passive display down here, and so you can use high-powered lamps to then create as large of a display as you want, and so it had advantages for this large screen display. The refresh time and a bunch of other things led to it not being viable, and of course LCDs and optical LEDs changed everything. But for a period of time, this darkening of alkali halides was quite a field of study. And Royce, who was actually here at Princeton, examined what exactly occurs within the salts. And I won't go into great detail here, but what happens is as an electron or ion comes into an alkali halide, like sodium chloride or potassium chloride, you end up trapping an electron in an anion vacancy. And there's also a lot of interesting quantum mechanics that can occur there, where you essentially have these salty harmonic oscillators. Wave equation, the wave function here, the root 6 has to do with the fact that the electron is surrounded by cations. And all of this leads to experiments that I conducted in my lab a number of years ago on alkali halides. And this brings us back to Europa's ocean, where I mentioned the magnesium sulfate as a solution, literally a solution for Europa's ocean, but magnesium sulfate doesn't last long in oceans. It gets drawn out as water cycles through rocks. The magnesium gets incorporated into various phyllosilicates, et cetera. But what does last long is alkali halides, things like sodium chloride and potassium chloride. And if Europa's ocean is in fact long-lived and cycling with the rocky seafloor, we have every reason to expect that alkali halides would also dominate that ocean. So in my lab at JPL, I create Europa in a can. This is an electron gun and a cryostat, young compressed cryostat, and I can do all sorts of vapor deposition stuff. But for these experiments, I put in some sodium chloride, which spectroscopically, sodium chloride and potassium chloride are horrible. They're just flat. There's essentially no spectroscopic features of any utility. And we, of course, know that just from our own experience with sodium chloride. But you put it in and irradiate it. And this is a video taken from one of the experiments I did on a evaporite of sodium chloride. And you pull it out, and you've got all of these trapped electrons in these F and, as I'll show you, M centers, these little electrons oscillating around in their S&P states that then lead to specific absorptions that cause a discoloration. In this case, it's kind of a yellowish brown. In some cases, it's a little more red or violet. And that comes back to your question about connecting to the Linnea themselves. And so when I first pulled those samples out, I was astonished by the connection to some of the colors that we had seen on Europa. Unfortunately, Galileo did not have any spectra at those visible wavelengths where these color center absorptions occur. The camera shown here with the color filters, the Galileo camera, color filters are shown there in the color bars. Not very useful for that initial publication, but you can see that the irradiated brine and grains plus H2O comes much closer to the, at least the color images than either the MgSO4 or the NaCl shown up at the top. Now, after I did those experiments, Mike Brown and I enlisted brilliant grad students, Samantha Trumbo, who then managed to get us time on HST to make observations of Europa with STIS. And beautifully, what Samantha was able to find is the absorption at the F center, that 450 roughly nanometer absorption of the trapped electron in sodium chloride. She didn't see the M center. The M center is the combination of two F centers, so essentially a pair of electrons coming in and occupying a larger anion vacancy. So we think we have the smoking gun of sodium chloride on Europa's surface by merit of the irradiation that the surface ice experiences from Jupiter's magnetic field. The fact that we did not see the M center, well, let me back up here just briefly. Samantha mapped where exactly that F center occurred. We were able to constrain it to this particular region on Europa, which actually does have more of a yellowish hue to it than the reddish color. Now, that region, as you see, is quite large. It's not necessarily right along the Linnea. I would say, in reference to your question earlier about what exactly is happening right along that small scale of the Linnea, I feel confident enough now to implicate endogenous salts, but that's not the end of the story. And so we're not going to have spectroscopic resolution at the scale sufficient to resolve the fractures until we get back out there with subsequent spacecraft. But at this point, I think this is the best indication of water rock chemistry in a salty ocean below Europa's icy shell. The fact that we did not see the M center, so on the left here, this is from an experiment that my former postdoc did, looking at the growth of these two absorption features, where again, the F center is the primary electron gets trapped, the M center is over time, you get a couple of electrons coming together. And you see that first the F center grows and then the M center. The fact that with Hubble, we didn't see the M center, we thought might allow us to use the band ratio as a geologic clock for how long that surface material had been exposed. And sure enough, you can use it as a clock. It's a very short clock. It only lasts for perhaps decades to centuries, perhaps as long as a millennium, but not over kind of geologic scales of millions of years. So for now, this is the highest resolution image that we have of Europa. The cliffs here that you're seeing are perhaps 100 meters or so high. This is a grayscale image. The dark material here that you see, I'm convinced has at least some composition of salts from the ocean below. Could some of it also be organics or indications of life from the subsurface? Perhaps when organics are irradiated, you do form a reddish material, but we're a long way off from making any conclusions along those lines. So I'll finish with just a few slides about what's next from a mission standpoint. The Europa Clipper mission is approved by NASA and just entered phase D. And with any luck, we'll get to the launch pad in 2024. As I mentioned, ESA has got the Jupiter Icy Moons Explorer. This will be launched in, I believe the latest date is 2026. It will go out to Jupiter, arrive there at about the same time as Clipper, late 2020s, early 2030s. It'll make a few flybys of the moons and then go into orbit around Ganymede. We also have a New Frontiers mission that I'm a co-eye on this called Dragonfly that will head out to Titan. It will parachute through Titan's thick atmosphere, then get rid of the parachute and start up its octocopter mode and descend down under the surface in a drone-like configuration. And then we'll do surface operations and then hop along the mid-latitude regions to various areas to investigate primarily the dunes and some of the ancient river networks. We probably won't get to any of the lakes, but nevertheless, this is quite an amazing mission that's approved and moving forward.
What is the energy source?
It's got an RTG, a radioisotope power source on the back. You can see it here, there.
Is there an orbiter as well, or does it?
No, this is going in hot and then doing direct to Earth communications. That's the big circular dish that you see on the surface here. And then not approved, but a mission that's taken up a decent chunk of my both professional life and actual biological life at this point is the Europa lander, which we had moved forward through what's called mission concept review and Delta mission concept review back in 2017 and 2018. And then we got put on hold due to various decisions and budgetary reasons. But this is a mission that would hopefully be launched not too long after Clipper and would land on the surface and use the robotic arm to investigate the ice, have a seismometer package on it to also listen to Europa quakes. As I mentioned, we went through these various reviews. You can find more information about the mission at these websites. We use a sort of smaller version of the Mars sky crane to come down to the surface. And then the primary science goals are to search for signs of life and engage in kind of comparative oceanography, trying to better understand the character and composition and geophysics of Europa's ocean. We've actually made a lot of progress in the hardware development. Some $300 million has been invested in this mission so far. And we'll actually find out at least some of the fate of this mission when the National Academy's decadal survey comes out on April 19th and prioritizes the next flagships for NASA. There's a lot of great science and great missions that compete against this. So my fingers are crossed that we're allowed to move forward. Okay, so I'll conclude by just harking back to Galileo. We all have seen this image before and know and love it. Jupiter at the center and the four stars of Medici as they were originally denoted around Jupiter. And of course, with Galileo's observations, we've come to appreciate that these are not stars, but rather moons. And with that discovery, Galileo would help put the nail in the coffin of Aristotelian cosmology and open the doorway to the Copernican revolution. And in the decades and centuries that would follow, we scientifically would come to appreciate that the laws of physics work, not just here on Earth, but also on worlds and wonders beyond Earth. And then with the advent of spectroscopy and better telescopes, we've come to appreciate that the principles of chemistry work beyond Earth. And with the robotic space age and our exploration of the moon and Mercury and Mars, et cetera, we've come to appreciate that the principles of geology work beyond Earth. But when it comes to that fourth major science, if we think about physics, chemistry, geology, and biology, we have yet to make that leap with biology. We don't actually know whether or not biology works beyond Earth. We have every reason to expect that it does, and of course we can send people into space and they still live, et cetera. But we have yet to find a second sample of biology working. We don't know whether or not life on Earth is some sort of biological singularity or whether or not we live in a biological universe. And part of what excites me about the time in which we live is that for the first time in the history of humanity, we have the tools and techniques and capabilities to answer this truly fundamental civilization scale question. So thank you for your time. Sorry, I went a bit over, but much appreciated anyway.
Explain a bit more how a magnetic field of the host of planet playing a role on their moons.
Yeah, how the induced field occurs?
I mean, so you show some pictures, some drawing pictures. So how the magnetic field from the planet that, what is the effect of the magnetic field on these features on the surface of moons?
Okay, so with respect to Ganymede, yes. So let me just provide a little bit of context for that. As some of you might appreciate, this is an old lithograph that I just scanned in from years ago. Here's Jupiter. Here's Io, Europa, Ganymede, and Callisto. Jupiter's magnetic field is tilted by about 9.6 degrees relative to the plane in which the moons orbit. And what this means is that as Jupiter rotates, the magnetic field sweeps past essentially at an angle. And so there's a dB/dt associated with that rotation. And the B field has a synodic period at Europa of 11.2 hours. And that's what gives rise to the induced magnetic field. Now, as that's occurring, there are electrons and ions that are bouncing up and down along these magnetic field. Some of those ions are sourced from Io, like the sulfur. Some, like the protons, are sourced from the upper atmosphere of Jupiter. Electrons come from both sources. Some of it's even solar wind particles coming into the Jovian system and then getting captured. As they sweep by Europa, there's a dropout that occurs on the trailing hemisphere of Europa from the magnetic field deposition of the ions and electrons. At Ganymede, because Ganymede has a magnetic field of its own, it actually directs some of the charged particles down along the magnetic field pole lines, somewhat similar to what happens here on Earth with the aurora, right? The whole reason that we're safe from solar wind is because of Earth's magnetic field, and we get the aurora up in the North Pole, et cetera. Now, Ganymede doesn't have an atmosphere, and so the atmosphere isn't there to take in that charged particle bombardment, but at least the magnetic field lines redirect some of that surface irradiation to the polar regions. And so you see a bit of a difference in the production of things like hydrogen peroxide and variations on methods of crystalline waters in the polar regions relative to the mid-latitudes. Does that make sense?
Yeah, interesting.
Yeah, the dynamics of kind of the radiation footprints and just the fact that volcanism on Io. So biologists love sulfur. Sulfur, or I shouldn't say biologists, microbes love sulfur. So microbes will eat all kinds of sulfur, from reduced H2S to oxidized sulfates. And there's a spectrum that microbes love to eat. And so just think about it, on Europa, some of the sulfur that might get delivered to the ocean that microbes might then chew on comes from volcanism on Io, this entirely other world. And so because of that tidal dance and the eruptions on Io, sulfur-eating microbes on Europa might be sustained.
Is it at all something to be thinking about, somehow get to this ocean, like melt the thing or something?
Yeah, that is the dream of dreams. Let me see if I actually have that is the dream of dream missions. And when I was younger, I thought it might get done in my lifetime. This is actually a video from I was involved with a IMAX thing many years ago. This was done in 2003. Back then, we thought we were going to have this very large spacecraft heading out to Jupiter that would carry a spacecraft. In reality, we were only going to land, but in this animation, you'll see kind of the vision for a melt probe, where you need some sort of radioisotope power source that can help you melt or drill through the ice. You'll leave behind a fiber optic cable and potentially some acoustic sondes that you can relay information back up to the surface. Once you get to that ice-water interface, the nose cone comes off, you deploy a highly autonomous underwater vehicle. Not going to be able to joystick this thing. And then, at least in this highly creative vision, which involved James Cameron, we get down to the hydrothermal vents on the bottom of Europa's ocean, discover not only shrimp and hydrothermal vents and microbes, but then we made contact with aliens that this predates Avatar, and you can imagine some of that, some of his time down at the bottom of the ocean fed into a lot of his sci-fi brilliance.
How much does this cost?
That's where the rubber meets the road. Yes. So the lander, which does not melt, the lander that I showed you, that's been costed at about 2.6 billion. I think we could actually do it cheaper by implementing a few variations, but that 2.6 to 2.8 billion number comes through a number of independent cost estimates that are the sort of NASA formally use. A melt probe, I would say, is in that kind of $10 billion range. Yeah. Which, like, I'm not bashful. Like, when it comes to spending on great discoveries, obviously JWST, tremendously excited about that. I think scientifically, we're very fortunate to be able to do what we do, but we don't necessarily need to be as bashful about the cost of these things, especially when you look at these costs compared to, say, military costs and developments of new fighter jets and what those price tags are.
That video is amazing. You were not able to convince people.
Well, for a period of time, we did have a number of folks convinced, and these missions often take a perfect alignment of congressional interests, scientific interests, the right people in leadership positions, and sometimes that all comes together, and sometimes it all dissolves. And you can imagine over the past however many years, there's been a decent amount of dissolution that occurred in the mid-2010 timeframe. In the 2016 timeframe.
Can I ask you a more technical question about this salt deposits and how they, under the electron irradiation, they change color and so on. So in what you were saying, is this different lines appearing and not appearing, it sounded like this has to be a young sort of young stuff out from the ocean, but then the whole ice surface is kind of relatively young as well. So that means that this salt should be everywhere,
right?
And then it should have been you would have longer irradiation away from these crevices, and so you would be seeing stronger signal, and you don't see it, and you don't see coloration. I mean, does it actually saturate this time if you bombard it for very long? Then does it become white again?
No, it doesn't become white again, but you can anneal through heating, and so. My experiments were done at 100 Kelvin, which is a good kind of average temperature to consider for Europa. But if you're at 180 Kelvin, which is a temperature comparable to the tiger stripes on Enceladus, then you've got a combination of, it's harder to retain those F centers at the higher temperatures. Now, related to this, when I mixed in, and I haven't published this yet, but adding a little bit of magnesium changes the visible color from a yellow to more of a white color. The spectroscopic features persist, so I can detect them spectroscopically, but visibly when I pulled it out, this was magnesium chloride coupled with potassium chloride coupled with sodium chloride. And I did this experiment with the ratio of those cations, sodium, potassium, and magnesium, at the same ratio that's found in our own ocean. When I pulled that sample out, it was white in color, but I could still see the spectroscopic signatures of the F and M centers. And so I think that, to your question, well, first, that the paper that I showed by Trumbo et al. Shows this distinct large-scale footprint, that yellowish region. We're still trying to understand exactly why that region retains the color centers and other areas do not. It may be as simple as that region does not receive as much sulfur from Io, and elsewhere on the surface of Europa, sulfur may mask the signature of the color centers. So that's kind of hypothesis number one, is just sulfur obscures the ability to see the irradiated salts. And that yellowish region is kind of on the leading hemisphere where less sulfur gets deposited. So it's a pretty viable hypothesis. But coupled with that, once you start adding other cations, you start to, in the case of magnesium, turn the color back to white. In the case of potassium, turn the color more violet. And so I think the actual answer to the story is going to be, not surprisingly, a salty mixture that can be seen preferentially on the regions that don't have as much sulfur deposition and that also have higher irradiation. So I know that's somewhat of an unsatisfactory answer at this point in time, but that's that's kind of what we're limited with. JWST will potentially be able to answer some of these questions, but really it's going to require us to wait until the Clipper and JUICE missions can get out there to really get the spatial resolution we need. The Juno mission, I should mention, so Juno's in orbit around Jupiter right now and has been operating beautifully. And in part of the extended mission for Juno, it's going to fly by Europa. I think the latest on this flyby that'll occur in the fall, early winter time period is it's going to be within about 300 kilometers of Europa's surface. And it will capture images of Europa. It's unclear whether or not the instrument on board, that's the spectrometer, is going to provide much useful spectra, but at least we'll get some tantalizing images. And we'll have to wait till clicker to find these beautiful jellyfish in the alien ocean.
Any more questions? Well, yeah, but so we wanted to ask that if you have this mission to the surface of Europa, and you've got these things coming out of the ocean. So what is a specific signature you find that could show what is there life in the ocean that has left something on the surface you can find?
Yeah, that's a great question. And we've got a whole report on exactly the number of biosignatures. Yeah, I don't have any other slides on this deck, but sorry, I keep on moving away from this. So first and foremost, you're looking at trying to have a robust array of what you classify as biosignatures so that you can design an instrument suite that can measure chemical biosignatures and morphologic biosignatures. Morphologic is just looking for structures, looking for, say, microbial mats within the ice itself at the larger scale, and then taking a sample and looking microscopically at the sample for cell-like structures, compartmentalization, things that are indicative structurally of life. And there's a variety of morphologic indicators that we use here on Earth. I've also guided our search for life on Mars. Within the chemical side, you can break it down into searching for organics. That's one of the keys, obviously. There are also inorganic indicators. One of my favorite inorganic indicators of life on Earth is marble. So marble, much of the marble that you find around our planet is a biosignature. But of course, when you look at marble, all you see is the beautiful stone that we like to carve and make statues out of. But marble once upon a time was limestone. The limestone once upon a time was precipitated out of an ancient ocean. That limestone derives from the shells of the calcite shells of foraminifera, these ancient things that lived and died on Earth in ancient seas. And so over time, the diagenetic processing turned these beautiful shells into just this stone that has no indications of past life. But you can look at the carbon isotopic signature of marble and tie that back to the foraminifera shells. Life on Earth is isotopically light with carbon. So we preferentially incorporate more carbon-12 and reject carbon-13 into our systems than geology does. And so when you look at, say, marble that is derived from life, you see it is enlightened in carbon-12. So isotopic signatures work both with inorganic and organic. And then within the organic, we'd be looking for things like lipids, things like large complex aromatics, amino acids at the dissecting not just the presence of amino acids, but also the specificity of amino acids. There are some amino acids that we see in meteorites, some that we see in life, and in the Venn diagram of those, there are a few amino acids, like I believe histidine, that are predominantly found in biology and not abiotically. So there's a suite of organic compounds that we would look for. And within that suite of organic compounds, you look for the specificity, things like the amino acids, things like fatty acids, things like nucleobases, but also without having to know of a specific compound. You could also just look at the mass spectrum and see whether or not it's a Gaussian or Poisson distribution versus a distribution with a very distinct specificity. Abiotic processes like Fischer-Tropsch type reactions that occur in hydrothermal vents generally produce a Poisson distribution of small chain organics. Biology does more of a picket fence. We use amino acids, and then we link those amino acids into peptides. We link nucleobases together to form our DNA and RNA, and we link our fatty acids together to form things like our membrane lipids. So even without knowing which specific molecule you want to go after, the broad character can also help you tell the difference between biogenic versus abiogenic. Then you would also look at the isotopic signature, and then potentially even chirality, looking at the handedness of amino acids and other chiral molecules. Life on Earth, our amino acids are all left-handed, our sugars are right-handed. Were life elsewhere to utilize amino acids, it would probably also early on have to make a choice about going left-handed or right-handed. There's no real reason to go either way. There's some stereochemistry stuff with interstellar gases that indicates perhaps there's a preference and abundance for left-handed amino acids. But you could look at the chirality of organics on the surface of Europa as a potential biosignature also. And so when we did this for the Europa lander mission concept, we had 9 different specific biosignatures, which were both complementary and redundant. And each of the instruments that made those biosignature measurements could also make, each instrument was able to make several kinds of biosignature measurements. That way, heaven forbid one instrument fails, we can still make at least several of the measurements in that 9 biosignature framework. So sorry, that was perhaps more information than you wanted, but there's a lot of information out there on this.
Yeah, I remember there were some questions in Zoom. Somebody from Zoom want to ask a question, please unmute yourself and speak up. No question. All right, so if not, let's thank Kevin again.